Hey everyone, welcome. Today we're diving into a really beautiful mathematical puzzle. It starts with something you learned in grade school, simple fractions, but it's going to lead us right to the edge of a massive, unsolved problem that's been around for 100 years.
So it all kicks off with a pretty simple question. You know when you type a fraction, like 1/7, into your calculator, you get that endless string of digits that just repeats? How long can that repeating part actually get? I mean, is there even a limit?
All right, let's start with the classic. 1 divided by 3. You get 0.33333 forever. The repeating block is just that single digit, 3. So we say its period length is 1. Easy enough, right? Okay, but now look at 1/7. This is where it gets really interesting. It spits out this beautiful 6-digit block, 142857, that just loops and loops forever. Its period length is 6. Now notice something here? The denominator is 7 and the period is 6. That's as long as it could possibly be. But hold on, it's not always so straightforward. Take 1/13. You might think, okay, maybe we get a 12-digit pattern. But nope, we get another 6-digit one. So the length isn't always just the denominator minus 1. And this is where the real mystery starts.
So what is it that actually determines the length of this pattern? This isn't just a fun little quirk, it's a really deep question in number theory, and it's got a formal name.
The technical term for this period length is the multiplicative order, and thanks to a super famous rule called Fermat's little theorem, we know there's a hard and fast ceiling. For any prime number p in the denominator, the length of the repeating part has to be a divisor of p minus 1. That's the absolute maximum it can be.
And this really sharpens our focus. For a denominator like 13, the maximum possible period is 12, but the actual one is only 6. It doesn't hit the ceiling. But for 7, the max is 6, and the actual period is 6. It goes all the way. These special primes, the ones where the pattern is as long as it can possibly be, are called full repton primes. And let me tell you, finding them is a very, very big deal.
In fact, this whole quest is at the very heart of a famous and still unsolved mathematical conjecture that's been stumping the pros for nearly 100 years.
It's called Artin's conjecture. For what we're doing, regular base 10 decimals, it basically predicts that there should be an infinite number of those special full repton primes. But here's the thing. To this day, nobody has ever been able to prove it.
So this is where the paper we're exploring today comes in with a totally fresh approach. Instead of trying to attack the problem head-on, it asks a different, kind of clever question. Which fractions set a new record for the longest period we've seen so far?
Let's walk through this method. It's called the record filter. We start with the smallest denominator, 3, which gives us a period of 1. Okay, our first record. Now what's the next smallest number that gives a longer period? That's 7, with a period of 6. New record. After that, it's 17 with a period of 16. Boom, new record. Then 19 with a period of 18. See the pattern? We only care about the next number that shatters the old record.
And when you do this, an absolutely stunning pattern just pops out. I mean, it's wild. First, every single one of these record breakers is a prime number. And not just any prime. Every single one of them is a full repton prime. The period is always the maximum possible length, p minus 1. It's like this filter is a perfect machine for finding exactly the primes Artin's conjecture is all about.
So you have to be wondering, does this sequence of record breakers ever just stop? Well, the paper gives a definitive answer on this. And it is a big one.
The answer is no, it doesn't stop. The paper proves that this sequence of record breakers goes on forever. You can always find another prime out there with an even longer repeating decimal pattern. There is no longest period. So the length of these decimal patterns just keeps growing and growing, heading off towards infinity. So wait a minute. If we found an infinite sequence of primes, and every last one of them is a full repton prime, that has to mean Artin's conjecture is true, right? We did it!
This just seems like the most logical conclusion. We've got an infinite line of record breakers, and they're all the exact primes we were hoping to find. So does this finally, after 100 years, prove the conjecture?
No. And this is the central, absolutely shocking twist of this paper. Proving that the period length grows forever is not, and I repeat, not, enough to prove that it hits that maximum value infinitely often. So why not? How is that even possible? Well, because there's a hidden trap. The paper uncovers this fundamental disconnect between the idea of just growing forever and the idea of actually hitting that ceiling. It's something called the separation theorem. What it says
in simple terms, is that unbounded growth, the periods getting bigger forever, and infinitely frequent saturation, the periods actually hitting their maximum possible length, are two logically separate things. Proving one tells you absolutely nothing about the other.
Think about it like this. Imagine a race car that can just keep accelerating, always beating its last top speed. Its speed grows without any limit. But what if that car has a built-in speed limiter that always caps its speed at exactly half of its theoretical maximum? It can keep going faster and faster forever, but it is structurally prevented from ever reaching its true top speed.
Well, the paper shows there's a mathematical version of exactly that speed limiter. It applies to an infinite set of primes that have a special property. They're called quadratic residues. For these specific primes, the ceiling, that maximum possible period length, gets automatically cut in half. It can never be p-1. The absolute highest it can ever go is p-1 divided by 2.
And this is the heart of the trap. You can have an infinite series of primes whose decimal periods grow larger and larger and larger off to infinity, while at the very same time being permanently blocked from ever reaching their true maximum length. Growing forever and hitting the max are two completely different ballgames.
So what does this all mean? The paper doesn't prove or disprove Artin's conjecture, but it does something that's arguably even more important. It stops future mathematicians from walking right into this elegant trap, from thinking that just proving infinite growth is enough. It basically gives us a much smarter map of the territory, showing us exactly why this problem is so incredibly hard.
And it leaves us with this really powerful thought. We started with something we all learned as kids, simple division, and it led us down a rabbit hole into a structure so deep and subtle that it has stumped the brightest minds for a century. It just makes you wonder, right? What other simple ideas that we take for granted are just hiding some complex, beautiful truth, waiting for us to look a little closer?